Hi everybody, welcome back to the section 3.2 video. In this video, we're going to take a look at a logistic growth model, particularly a spread of disease model, which is a nonlinear differential equation. So let's see what this question is asking us. So suppose a student carrying a flu virus returns to an isolated college campus of 1,000 students. If it is assumed that the rate at which the virus spreads is proportional not only to the number X of infected students, but also to the number of students not infected, we want to determine the number of students infected after 6 days if it is further observed that after 4 days, 50 students are infected. Okay, so a couple of things from this question that we can pick apart, mainly that the real question here is that after 6 days, how many students are infected out of this 1,000? Okay, so this situation of spreading of a virus or disease, we've actually seen before in section 1.3. We've actually developed a mathematical model for spread of disease. So let's recall that spread of disease, the differential equation, the mathematical model for that we developed was dx over dt equals k times x times n minus x. And we have an initial condition at time 0, we have 1. And this 1 represents one person being affected or patient 0. And this is a non-linear differential equation. Why is that? Well, because if we distribute in that x, we'd have an x squared, and your dependent variable squared makes this non-linear. Okay, so let's fill out a couple things. N represents the total number of people in the community. So what we can have is, say, 1,000 is N. So we can substitute in N to be 1,000. So dx over dt equals k times x, 1,000 minus x. And let's write our initial condition still. Okay, so what else can we say that our differential equation looks a bit familiar to something we have covered in this section already? So why is that? Well, let's distribute in this k. Let's distribute in k and see what happens. dx over dt equals x times 1,000 k minus x times k. Initial condition is still the same. Well, recall the logistic growth model. Okay, recall the logistic growth model. That's dp over dt equals p times a minus b times p. So we have a couple things we can pick out. We could see that 1,000k is a and k is going to be b. And recall the solution to a logistic growth model looks like this. It is P of t equals B times P naught in the denominator plus A minus B P naught times e to the negative AT, and we have A P naught in the numerator. So we can actually start plugging in things we know into our solution. So we know 1 is P naught because that's our initial population, patient 0. And we know what A is. We know what B is. So we can start plugging in some values here. So let's go ahead and try that out. So thus, solution to this differential equation of spread of disease is x of t. 1000 K, just literally plugging it into here. 1000 K times 1 over K times 1 plus 1000 K minus K times 1 e to the negative 1000 K t. And just remember that A equals 1000 K, B equals K, and P naught equals 1. So we could simplify this down quite a bit to make it much better to look at. So top would just be 1000 K. The bottom would be K plus 999 K e to the negative 1000 K t. And you can simplify this even further. Notice how we have K's in both terms in the denominator. So let's factor that out. We'll see why in a second. So we're left with K times 1 plus 999 e to the negative 1000 kt. Well, we would do that because the K's could then cancel out. And so what I'm left with is 1000 over 1 plus 999 e to the negative 1000 kt. Okay, so let's go ahead and use this solution that we found. And now we're going to find K. And in order to find K, we're going to use what we're given from up above, that at 4 days, there's 50 people infected, and use that to find K. So use x of 4 equals 50 to find K. So let's plug in what we know. 50 equals 1000 over 1 plus 999 e to the negative 1000 K times 4. Okay, so we've done this quite a couple of times, but I want to see if you guys can try it out. So pause the video and go ahead and see if you can solve for K. Okay, welcome back everybody. So hopefully you got that K is approximately 0.00991, somewhere around this decimal. So hopefully you did all the right steps. Let's kind of backtrack a bit just to make sure. So this is what we started off with right here. before you tried it out, hopefully. But then you just want to solve for K. So what we did was combine negative 1,000 times 4, so negative 4,000. And then we just started trying to solve for K. So what we did was multiply both sides by 1 plus 999 e to the negative 4,000 K to both sides. And so we then divided both sides by 50. That became 20 on the right-hand side. Then we subtracted 1 from both sides to get 19 divided by 999. Natural log both sides. Solve for K and simplify to 0.0009991. So what we do is take this K, this proportional constant, and we take it, plug it all the way back up here to where we first started with our solution. So when we do that, we get x of t equals, I'm going to start off with the denominator first, 1 plus 999 e to the negative 1,000 times that 0.000991 t. And this is all underneath 1,000. So we can simplify this a bit. Negative 1,000 times our decimal is going to start off with the denominator again. 1 plus 999 e to the negative 0.991 t. Okay, so this is our solution with our constant k. So what's the original question again? We've done a lot in this problem, but what's the original question? The original question is after 6 days, how many students are infected? That's the original question. So we have our solution. So finally, we are going to figure out how many students are infected after 6 days by just plugging in 6 into the solution we just found. 1 plus 999 e to the negative 0.991 times 6. And essentially, we throw this in your calculator, we get approximately 276 students. So therefore, after 6 days, approximately 276 students have the virus or are infected. That's a better statement. So that's how we would use a logistic growth model for something like a spread of disease. Okay, so a lot of work in this problem, getting to this final point, a lot of calculations, a lot of identification. But remember, the key points here are that we had a logistic growth model and we know how to solve a logistic growth model. We have the solution for us, and we were able to pick apart what A would be, what B would be, and what P naught is, and be able to put that in our solution and figure out K, and then use K to figure out what the original question is asking. So thank you for watching this video. Hopefully, we're able to get all these steps, and take care. I'll see you in the next one.